Alright guys, so today we're going to talk about intersections in space. So remember, we're going to have our three-dimensional space. We're going to have x, y, z coordinates. And we're going to look at intersections of lines and planes, planes and planes, lines and lines, and all sorts of objects. But firstly, if you have a line, the first question is a point on the line or not? That would be the intersection of a one-dimensional object with a zero-dimensional object, namely a point, in fact. So let's say that you have a line of the form x equals 3t minus 1, y is going to be t plus 1. Let's just give numbers. Z is going to just be t. Let's do something like that, and let's ask, is the point one comma 1, I suppose, just any point on the line. All right, so let's see if that is the case. So what you would do is you would set your x coordinate equals to the x coordinate that you're given. So in this case, x is going to be 1 equals 3t minus 1. Then you would set the next one, which is going to be 1 for the y, equals to t plus 1. And lastly, you would do 1 for the z. It would have been a little bit better to use different numbers so you would see where each goes, but I'm just grabbing the x coordinate, setting equals to x, y coordinate equals to y, and so forth and so on. And then the last one would be z equals to t, which is 1. So that automatically tells me the value of t that I would have to have. And if I plug t here equals to 1, I would get 1 equals 1 plus 1, 1 equals 2, which is not true. So if I evaluate this equation with what I obtained, that would give me a nonsensical situation where it would be 1 equals 2, but we know that is not equal to that. Since, by the way, I should have had a question mark here, and since the system of equations had a nonsensical answer, then I would say no, the point is not on the line. Okay, so now the question is, well, what happens whenever, or how do I recognize when something is indeed on the line? So let's go ahead and take a look at that. Let me erase here. I'm going to put another point, and I want to look at one where it actually works. Okay, so now in this case it's going to work out. I force it to be. So let's do the same thing again. Is the point 2 to 1 on the line? So let's go ahead and put x equals to 2, which is going to be equal to 3t minus 1, y equals to 2, t plus 1, and then z, which is going to be 1 in our point here, is going to be equal to t. Again, very artificial. I forced it to work, but that's how it's going to go. The only thing is you may have to solve a little bit more, but notice that if I plug in here the value of t equals to 1, I get 2 on right hand side equals 2 on left hand side. If I plug again my t equals to 1 on the first one, I get 3 times 1 is 1 minus, sorry, 3 times 1 is 3, minus 1 is 2, so 2 equals 2. So all the solutions, all the equations are satisfied when t is equal to 1. So since all of them are satisfied at t equals to 1, yes, the point is on the line. So now the next question will be, what if we have two lines that are given in parametric form? How do we determine whether they intersect or not? And my space here is still waiting to something to be plotted, but we'll do that soon enough. Or actually, you know what? Let's look at the graph of this one. So how would you graph this right here? And I want to grab a vector, important vector here with the coefficients that are in front of my t, which are going to be 3, 1, 1. So I'm going to look at the vector 3, 1, 1. And that vector is going to be the director of that line, because notice that it's going to be a multiple of that vector plus the vector. So you can write in vector form, if you will, like 3, 1, 1t plus the vector -1, 1, 0. So I'm going to look at this vector first, and then I'm going to shift by this. So when you write the equation in vector form, what that tells you is that this the line is going to be basically multiples of this vector. So they're going to be going in the direction of that vector 3, 1, 1, and then you're going to be shifting it by -1, 0. -1, 1, 0, sorry. So let's draw this vector first. So let's go ahead and do that. In the x-coordinate, I need to go to 3. There. In the y-coordinate, I'm going to go to 1. So just there. So I'm going to be here, a little far. There we go. So it's going to be 3, 1, 1. And then I'm going to go 1 up. So roughly this up. And my vector 3, 1, 1 is going to be the vector that goes in this direction. Like that. Okay? So that's the vector 3, 1, 1. So it comes out towards me. Yes, I dropped the marker. I'll be right back. So as I said, it comes in my direction. But now, the line is going to be the multiple of this vector, or the multiples of this vector, but it's going to be shifted by the vector -1, 1, 0. So let me look. I'm going to draw in orange. All the multiples of this vector are going to be basically going in this direction, just continuing the vector. That's going to give you a line, which would be the line 3t plus t plus t. Sorry, 3t, t, t, which is going to be 3, 1, 1 times t. Now I'm going to shift it by the vector -1, 1, 0. So let's go ahead and draw that vector, -1, 1, 0. So -1, I'm going to go to the back. 1 in this direction, so still here. And then 0. So I'm going to shift it by this. So what I know is that this line is going to be, or the line I'm looking for is this exact same line, but it's going to have to go through this point. So the line I'm looking for, the line given by these equations, is going to be the line that is parallel to this one that goes through this point. Let me focus as much as I can. Not really good. They're not quite parallel, are they? All right, well, you can use your imagination and visualize it, and I'm sure they look perfectly parallel. By the way, do you know what's really sad about parallel lines? They had so much in common. So bad they never met. Anyways, let me erase this, and then when I talk about intersection of lines, this never intersected. All right, so we started with one line, one dimensional, 1 point, 0 dimensional. Let's go up in one dimension for one of them. So one dimensional line with one dimensional line. Do they intersect? So how do you do it? Well, I'm going to draw a quick sketch. It's not drawn to scale or anything. Let's say you have a line here, and it's going to be parametrized. And you have here t equals 1, t equals 2, so it's going in that direction, t equals 3, or whatever. And then you have another line, and they do intersect somewhere here. However, this line goes in this direction now, and you have t equals 1. I don't want it to look like they're going to intersect at the same time. T equals 2, let's say here t equals 3 is here, t equals 4 here, and so forth and so on. Now, look at the lines. They do intersect. However, this line, it goes through the point of intersection at times equals 3, as opposed to this one. This one goes at the intersection point almost at times equals 4. What I'm trying to tell you is that whenever you're going to set, whenever you try to determine if a line or two lines intersect, you cannot just say, well, let me set x equals to x and y equals to y, because you would end up with an equation in terms of t only, and this would even give you a nonsensical equation. It would be t equals t minus 1. At that point, you get the t's cancel, and you get that 0 equals -1. That doesn't make sense. But that doesn't mean the lines do not intersect. What that means is they do not intersect at the same time. So if these two lines were describing the path of an object, then what you know is the objects are, each one of them an object, a different object. What you know is that the objects would not be colliding, but they would be going through the same point at different times, but they can intersect. Now, to determine whether they intersect or not, we're going to set them equal to each other, and when I try to solve the system of equations that results. Now, if the system has no solution, then you do know that the lines do not intersect. If the system has a solution, then they do intersect, even though the parameters may not be the same. So the question then is, do they collide? If this describes a particle, then for that you would need that the lines intersect at the exact same time parameter. So to solve it, how do you do it? Well, you grab the x for one, t minus 1, and you set it equal to the x of the other. However, you're going to change the parameter. Why? Because then you're not forcing them to collide. You're asking whether they intersect only. So you're going to call this one s, if you will, or whatever parameter you prefer. That's going to be one equation. Your next equation is going to be 3t plus 1 equals s plus 4. You see, I changed that t to s so that I'm not requiring them to collide, just to intersect. Then the z's, t plus 1 equals s plus 2. And now notice that this is a system of equations with 2 unknowns and 3 equations. So what can happen is overdetermined. So what can happen is that you obtain a solution for t and s in the first 2 equations, and then they're not going to satisfy the third equation. Or it may happen that you find a solution for the first equation, you find a solution for the first 2 equations, and then it satisfies this third one. So let's take a look at what happens here. So what I'm going to do, this one is perhaps easier to solve because I have simply an s. It's easier to solve by substitution. I can substitute s in here, which gives me an equation of the form t minus 1 equals, oh, sorry, I should have done 3t plus 1. Left hand side is 3t plus 1, and I'm going to plug s equals t minus 1 here. So t minus 1 plus 4. And so that gives me an equation that I can solve easily. 3t plus 1 equals t plus 3, and I can subtract 1 on both sides and subtract t on both sides, and I get 2t equals, what did I say I was going to do? Subtract 1, so 2. So that's going to give me t equals to 1. I may be running out of time, so I'm going to move out of space. Sorry, I'm going to move over here where I got t equals to 1. Okay, so that's going to be my value of t. Now I can obtain, if t is equal to 1 from this equation, I can just plug it in and get that s is equal to 0, because it's going to be 1 minus 1, so 0. All right, so now that is the solution that I obtained for this system of equations with equation 1 and 2. Notice that at no point I use equation 3. So what I'm going to do now is verify that equation 3 is indeed satisfied. If it's satisfied, then I know the 2 lines intersect. If on the other hand, I would plug this into this equation and it wouldn't be satisfied, then I know the lines don't intersect. I know they do intersect because I set it up that way. So plugging into 3, so I guess this is going to be equation 3, even though the other ones I didn't label. And so plug into 3, and what I'm going to obtain is that t, which is 1, 1 plus 1 equals, question mark, we don't know, 0 plus 2, but then you can verify that that indeed is true. So you have that 2 equals 2, so the last equation is satisfied, so the answer is yes. The lines do intersect. However, notice that this one goes through that point at t equals 1, and this one goes at the intersection point at t, which I changed to s, but is at times equals 0. So if I would ask you, do the particles collide? No, they don't. Do their path intersect? Yes, they do. And if this would have given you a nonsensical equation or a non-equal, then you would have that the paths simply do not intersect. All right, so that gives us our one-dimensional intersection. So now let's go up by one more. So let's make this a plane, and let's leave this one a line. I'm going to write the equations, and I'll be right back. All right, so now I have a line and a plane. This one is in parametric form as well. However, this could have been also given in terms of the general equation, so we got to be careful with that. So how, by the way, that gives me an idea. So how would you go from this form in parametric forms to the general equation? Well, you will have to solve for each parameter in terms of the x and y's, and then substitute them in. So for example, here, if I add x plus z, then I get x is t minus s plus t plus s, which is z, and that right there cancels the s. So I noticed that they're the same, just with different signs, so that's why I added them together. I could have used x and y as well, and that gives me that x plus z is going to be 2t. So I can obtain that t is equal to x plus z over 2, and so I get one of them. So now if I want to eliminate the t in this case and leave the z, I would the s, I would do z minus x, and when I put z, would be t plus s minus x, which is going to be t minus s. From where I'm going to have t minus t cancel, I get s minus negative, so plus s. So z minus x will be equal to 2 s. And as before, s is going to be equal to z minus x over 2. So using these two equations, I found t and s in terms of the other guys. I just have to plug it in here, and I get that y is going to be 3 times t, which is 3x plus z over 2. That's what we said that was t. Plus s, which we said is going to be z minus x over 2. All we have to do now is multiply everything times 2 and simplify, and we would get the equation, general equation of our plane in that case. All right, and it seems like this plane will actually, because I didn't put any, yeah, it seems like it's obvious because I didn't put any other terms here. This plane goes through the origin, so this is going to be an equation in terms of x and y and z equals 0. So that's how we would obtain our general form. So if it's given in general form, then to go backwards, you would basically grab one of the variables, say x equals t, and then y equals s, and then you solve for z, and you get your parametric form. So then once you have it in parametric form, whichever way it's given, you can then solve to find intersection of the line and the plane, as we're going to do here now. So I did a little bit extra there, but I don't think I mentioned that in the previous video, so let's go ahead and do that. Let me erase this part, and I'm going to go back to the intersection. A little bit delayed, but we'll do that. All right, so now that we have it in this form, the same thing as before. When I said the x equals to x, but we need to change one of the parameters. This time is a lot more convenient to change the first parameter, because here I have 2 of them. It's going to get messy otherwise. So I'm going to do the x's. So t minus s is going to be equal to, here I'm going to call it r minus 1. So I can feel like a pirate. So y is going to be 3t plus s. And that's going to be equal to 3r plus 1. And then here I'm going to have t plus s, which is the z, which is going to be equal to r plus 1. And so here I'm going to do kind of the same thing I did before. I'm going to go ahead and try to solve for t and s using 2 equations, and then I'm going to substitute in the oh, take it back, I have 3. So I'm going to have to try to solve here in general. Now, if you do know linear algebra, this is a lot better if you just write it in the following way. You just subtract all the variables in one side and then do your reduced row echelon form there. If you don't, what I just said doesn't make any sense, but I'm still gonna move it like I'm gonna put everything with variables on one side and all the parameters on one side and all the numbers on the other. T plus s minus r equals to 1. All right, so at this point we have to solve the system of equations. Notice here that I can eliminate the s by adding equation 1 and equation 3, and that will give me a new equation. So I can write t minus s minus r equals -1, and then when let's copy the next one. So 3t minus s minus plus s. Sorry, if you mess up the sign, then you're in trouble, I suppose. equals 1. And now I'm going to add these two equations. So I get 2t, and then when you add negative s plus s, they cancel, and then negative r minus r, so it will be minus 2r equals 1, negative 1 minus 1, which is going to be, did I add them? No, I added them. So negative 1 plus 1, which is 0. Be careful with what operation you're doing. This right here will tell us that then t is got to be equal to r. When I add 2r on both sides and divide by 2, I get that t equals to r. That simplified my problem quite a bit, because now I can substitute in t equals to r, and then I can solve from there. I think I'm going to erase here, and I'm going to finish the problem. Actually, take it back. I'm going to erase up here. I'm going to keep working kind of in a cascade so I can have my equations here. So I'll erase. I'll be right back. All right, so I'm back. So now substituting in the t and the r, since t is equal to r, this is going to be 0, and this is going to give me negative s equals to negative 1, from where I'm going to have that s is equal to 1. Am I too high there? I think I'm good. So s is equal to 1. All right, so as I said, when we plug things in, we get our solution. And by the way, we got s equals to 1, and we got r equals to t. Remember that our formula here was r was this variable. And now the problem is, now whenever you write everything into your system of equations, you're not going to have anything but this solution. What does that tell you? Is that the system of equations that we set up actually has infinitely many solutions. Any t and r will work. What does that mean? Well, that means that I was not careful to set up my my system, which is a good thing, actually. We are going to find something out that is rather interesting, and that is that the line actually is on the plane. So whenever you have infinitely many solutions to your system of equations, and if you plug things here, what would happen is that if you plug the value of s equals to 1 and leave r equals to t, what happens is that at s equals to 1, the equation of the plane becomes x equals, well, I was trying to match the numbers so there would be an intersection, and I didn't realize that I used the exact same coefficients. It would have been much nicer to use, say, 2t and 2s. Those would have worked with the numbers I was thinking about. And then you would have a unique solution to system equations, and it would have been okay. However, I chose this one, so that's what it is. So if you plug s equals to 1, you get the equations of the line, which if I would have been careful, I would have noticed, but that then tells you that the line is on, actually it turned out to be a good example, is on the plane. Plane 1. Now, I could have modified this problem, and I did play before I started recording again. And for example, you simply have to eliminate that dependence, that force t equals to r. So something like 5t minus s. That will give you that the line actually intersects, and it would happen when t is equal to s for this line, and that would have been equal to what value was it? 1, I think, is what we would have gotten, and then r would have been equal to let's see, would have been equal to 1 as well. Yes. So if you solve this system of equations, actually exercise, you can do it. And then what happens is that, how do you find the intersection point? You grab the parameters that you obtain and you plug them back into either the plane or the line, and you should get the same point. So the point that you would get is x would be t equals to 1, s equals to 1 would be 1 minus 1, 0. For the y coordinate, you would have 5 times 1, 5 minus 1, 4. And for the z coordinate, you would have 1, t equals 1 plus s equals 1. 1 plus 1 is 2. And that would be your intersection point. The same thing, by the way, I didn't do that with the lines. If you're asked about what is the intersection point, whatever parameters solve your system equations, you plug those into the equations of the line that you were given, and that gives you the intersection point. And it is a good thing to plug both of them to make sure that you actually get the same value. All right, we talked a little bit about plane intersection with plane in the previous video. And this video is already extremely long, so I think that we're gonna leave it at that. So thank you so much for watching, and I'll see you next time.